Hi guys. I'm gonna go over chapter 16 notes with you. I hope you are enjoying class. Um, don't forget before I start going over these that you have an online quiz this weekend. It will be on QuizStar. Make sure you're signed up. Make sure you take the practice skater quiz on QuizStar. Um, and if you sign up, I need to accept your registration. So it may take me like a day or so to check it and accept your registration. So make sure you're ready to go for the quiz on chapter 16 next weekend. So you guys will be taking the quiz between Friday and Sunday at 11:59 p.m. And I'll let you know more about that through text messaging. All right, so chapter 16. Chapter 16, we're going to talk about minerals, and just to remind you, minerals are considered non-renewable. So we've talked about renewable and non-renewable resources up to this point. So all minerals are non-renewable, meaning that once they're gone for good. And the first picture we see here on the slide is a picture of acid mine drainage. So this is a review. Don't forget, acid mine drainage is an orange/red liquid that seeps from mines that have been abandoned. And many times these mines have been left open, these surface mines, and the rainwater mixes with the iron and sulfur. So you can kind of see the reaction at the top of the slide. And we're going to end up with some sulfuric acid and dissolved iron. So this is going to seep away from many of our old abandoned mines. This specific one for this picture is showing you acid mine drainage from a mine in Leadville, and it's in Colorado. And this specific mine has been basically mined for gold, silver, lead, zinc for more than 100 years. And this acid mine drainage runs off into the Arkansas River. And so obviously this is a negative thing for the environment. The acid has a very low pH, it runs into the waterways, and fish and wildlife can only live in a certain pH. So if it's too acidic, basically biodiversity is going to decline, and we're going to have the death of the aquatic organisms. Okay, here we have some more pictures of some acid mine drainage. Make sure you know the definition of this. Again, this is a review because we've discussed this before in our coal chapter. So here you see a lady who is bending down looking at the acid mine drainage. No, that's not me. Almost looks like lava in some of these pictures. Okay, so the General Mining Law of 1872. So going back to the 1870s, the federal government basically enacted this law to get people to move westward. So because everybody in the United States was kind of congregated in the northeastern or the eastern part of the United States, in order to get people to move westward and to settle out in the western parts of the United States, the federal government enacted the General Mining Law. And you can kind of see the definition here. It allows companies or individuals, regardless of U.S. citizenship, to stake mining claims on federal land. Basically, it means that any person has the right to explore and extract minerals from an area of land that they think that has those minerals. Then they have to purchase the land for a fraction of the value. They extract whatever minerals they have there. It could be gold, copper, zinc, and then that company or person is allowed to keep all of the profits. And so this is very different than how fossil fuels work. To contrast with fossil fuels, when a company is going to extract them, a percentage of the profits ends up being paid to the federal government. And so it basically got people to move out west. As you can see for the second little bullet point there, there's no environmental protection in the law. And so basically people and companies, they would leave abandoned mines that were heavily polluted. So instead of reclaiming the land or fixing up the mine, they just left these abandoned old mines. And so obviously we have environmental problems associated with acid mine drainage, and everything became very polluted. So many of these mines around the United States are known as Superfund sites, and we'll talk a little bit more about the Superfunds law a little bit later on. You may have heard of it before, but basically it uses taxpayers' dollars to clean up old hazardous waste sites in the United States. Okay, so what is a mineral? Minerals are essential for us and for plants. We've talked about minerals for plants like phosphate and nitrate, so those are just some examples. But here's your definition. Inorganic elements are compounds of elements that occur naturally in the Earth's crust. Again, they're non-renewable, meaning that once they're gone for good. We can break down our minerals into metallic and non-metallic. So metallic minerals are going to be metals. Some properties or characteristics of metals is that they are going to be malleable or bendable. They're going to be lustrous or shiny, and they're going to conduct electricity. Many of our metal minerals have originated from igneous rock. And to give you some examples like copper, iron, and gold, those are examples of metallic minerals. Non-metallic minerals have the opposite characteristics. So they are not malleable. They do not conduct electricity. They are not shiny. Most non-metallic minerals originated from sedimentary rock. And some examples for you, you can kind of see on the slide here, we have some table salt. That would be a really good example. Phosphate, sand, those are considered non-metallic minerals. We also have two different types of ore. Ore is just a rock that contains a specific mineral. And if we have high-grade ore, that means that that rock contains more of that mineral. So if we could just talk about, for example, gold. You can see some gold in the bottom right-hand corner. So if we have a rock that contains a high percentage of gold in the rock, that's considered a high-grade ore. And if we have a rock that contains lower amounts, that would be a low-grade ore. And so obviously it's more economically profitable to extract and refine high-grade ores because you're just getting more of the mineral. Super simple. You should be able to contrast an ore and a rock. A rock is just a mixture of minerals, so it's a varied composition. Again, our ore is a rock that's going to contain a percentage of a certain type of mineral, whether it be gold, iron, zinc. Those are all examples. Okay, so here are some examples of some important minerals and what they're used for. You may not even realize the things that you use on a daily basis that contains these minerals. But we have to obviously be very careful with them. We need to make sure that we are using them efficiently and that we're going to recycle them because once they're gone for good. So if you look at going across the top, aluminum is an example. Think about all the things that we use aluminum. So all the way from packaging like aluminum foil to water treatment like aluminum sulfide, if you remember, parts of aircraft and cars. So aluminum is really, really important. We used to call it tin foil, so maybe you've heard like your parents or someone call it tin foil in the past. We don't even use tin foil anymore because tin has basically been extracted so much that now we have to use aluminum. Next one over, you can see chromium. Maybe you've heard of chrome. You can see it on a faucet right there. Maybe you've heard of like chrome rims. You know that those are a little bit more expensive than say hubcaps on someone's car. Chrome can be used to make steel. So it's going to make an alloy, which is like a mixture of metals, dyes, paints, cutlery. Cobalt, you can see the next one, you can see that blue glass there, it has a blue pigment. So if you see glass that has a blue pigment, many times cobalt is used. Gold, so obviously we know about gold, you probably think jewelry is the first thing. Maybe you've heard of gold trading, you know, that people buy and sell gold on some of those commercials. Gold can be used in our teeth. And iron many times is used to make steel. So it's an alloy of iron, and obviously steel is really important in construction and building. Magnesium, you can see it's in some of our beverage cans, electronic devices, firecrackers and flares. Mercury, we've talked a lot about mercury up to this point. We know that it is used in certain types of light bulbs, electronics, batteries, We've talked about the negative impacts of mercury when we burn coal, but mercury is actually extracted and used for things that we have in our everyday life. And then molybdenum, just another example, so used to make alloys. So these are just some of the important minerals and their uses. Okay, the rock cycle, how exciting. So think back to, I don't know, third grade when you go over the rock cycle. But basically you need to know the steps of the rock cycle. You can start anywhere because it's a cycle, so it's not a place to start. But we can start with magma just to have an idea. So magma rises from within the mantle and it comes up from the earth, and as it solidifies and cools, it becomes our igneous rock. The breakdown of igneous rock, or basically the weathering of any type of rock, is going to yield or give us sedimentary rock. So you can see the breakdown or the weathering of igneous rock, and also the weathering of metamorphic rock is going to give us sedimentary rock. If we have our igneous rock under high heat and pressure, then we're going to generate metamorphic rock. And after our sedimentary rock, because we kind of talked about weathering as the main process of forming sedimentary rock, heat and pressure and other chemical reactions are going to give us metamorphic. So metamorphic is formed by heat and pressure, sedimentary is formed by weathering, and igneous is just the cooling and solidification of magma. So please make sure that you look through this, that you have an idea of how each rock forms. Okay, so mineral distribution and formation. So important abundant minerals that are found in the crust. Again, just some more examples here. Aluminum and iron are both important abundant minerals. Um, Luckily we have this. That's why, again, we're able to use aluminum foil versus tin foil. Some scarce minerals, so these minerals cost more money. Copper, chromium, and molybdenum. So we have less of these minerals. Copper wiring, just to give you an example, in housing is pretty expensive. So there's been like some major like copper thieves in the past. Like, it's on the news if you ever um, listen or pay attention. So houses that are built, like as they're being built and the copper wiring is being put into the building, you have to be very careful because people will come and like rip out that copper, because you can sell copper and get a lot of money for it because it's so scarce. Again, chromium, you should think of like chrome rims, how they're a little bit more expensive than say like other types of rims. And molybdenum, those are all examples of scarce. Just like our fossil fuels, minerals are distributed unevenly across the world. So in some areas we find it in low abundances, in other areas in high. So you just happen to have to be like lucky as a country or region to have some of these minerals. Some places they may have some of these minerals, but because there's so little of it, or it would be too expensive, it's not worth it to extract them. And so this is just showing you the crust in case you forgot your layers of the earth. You have your inner core, outer core, mantle, and crust. And there's a question on an AP exam. You may have seen it already this year. I can't remember, but something along the lines of what is the most common elements in the Earth's crust. And so I just decided to throw that onto this PowerPoint slide since I have the crust here. And so 46.4% is going to be oxygen, and then 28.2% will be silicone. You can see the lesser percentages of the other minerals there. Alrighty, so this is showing you 9 important minerals and their distribution across the world. So you can see we have some copper in the United States, zinc, I know it's kind of blurry, lead, and so it's distributed unevenly. So certain areas or certain countries have more of minerals than others, just like fossil fuels. All right, so how do minerals form and deposit? Like, how do we end up having them in depths that are close enough for us to extract? So there's 4 main processes. The first one is called magmatic concentration. And if you look at this definition, basically it's when we have the layering of minerals. So as magma, it's going to move up into the Earth's crust. It's going to solidify and cool. we are going to have layered minerals that are going to basically harden and settle out. So many times we tend to see iron and magnesium, so you can see on the slide right there. They tend to be heavier, so they're going to kind of fall to the bottom of the layering versus silicates or silicone, which is going to be lighter, and so it's going to kind of be on the top layer. So one way in which we get minerals from within the earth to places where we can extract them is through magma. So the magma moves up and it's going to cool, and we're going to have minerals that are deposited close to the Earth's crust or in the Earth's crust. The next one is called hydrothermal processes. This is basically as heated water. Oops, sorry about that. So as heated water from within the earth, it's going to move up through the crevices and the cracks in the earth, and it's going to make its way closer to the earth's surface. Many times we're going to have minerals dissolve in the water. So certain minerals are going to be able to dissolve in the water, carrying those minerals closer to the earth's surface. Some minerals are not going to be able to dissolve in the water, so they're going to kind of settle out, especially when the water comes into contact with sulfur. So many times we get gold, silver, copper, and lead associated with hydrothermal processes. And so as it moves up, we're going to have access to these minerals. So heated water. Your next one is through the process of sedimentation. So this is weathering. So we talked about weathering, or the breakdown of rock, in the soil chapter. And as we have weathering of rock, it could be mechanical or it could be chemical weathering. As the rock is kind of broken down, we're going to have the release of mineral particles that many times is going to be transported by water. And we know that rivers are going to eventually empty into the ocean for the most part, unless we have like what we talked about, like a lake that ends up becoming salty. But the majority of our rivers are going to end up in an ocean, and so many of those minerals are going to make its way to the ocean. And so when the warm river meets the ocean, so think about that estuary area where the river meets the ocean, we're going to have specific minerals like iron and manganese kind of settle out. So two examples would be iron and manganese, and we tend to see them where the warm river meets the cold ocean. So that's how we end up with those mineral particles. And then the last one is going to be evaporation. So we've talked about this before with the RLC, with Mono Lake, and we've said that as water evaporates away, many times we have different types of salts that are left behind. And so this is how we're able to access some of these minerals. So some examples of minerals that would be left behind with evaporation would be salt, borax, and gypsum. Okay, and the last slide for this little video. Uh-oh. I don't know what's happening. Sorry. Okay. No, stay there. Okay. Discovering, extracting, and processing. So we have to discover where our minerals are located. We talked about looking for oil, if you remember, in natural gas, and we talked specifically about structural traps. Very similar process in order to find our minerals. So we have geologists, seismologists, all of these people who are working together. They are using aerial photos and satellite images. They are looking for certain rock deposits that they know are associated with specific minerals. They can use vibrations, magnetic fields, in order to try and figure out where we think minerals are located. That's kind of how we start to try and find it. So looking for geological formations. With Earth's magnetic field and gravity, we tend to see certain deposits of minerals. And we're really just making estimations and trying to figure out possible locations. And once we've identified where minerals are located, then the mining begins. So extracting, says here, it can be extremely destructive. We are going to use surface and subsurface mining that we're going to look at in the next video, but we actually have to rip up the ground and get the minerals from within the ground. And again, we're going to go into the different types of mines in our next video. And then processing by the process by smelting is basically how we are going to process these minerals. So it says smelting. We're going to melt the ore at high temperatures, and we're going to separate impurities. So we are going to take that rock, that ore that contains a high percentage of the mineral, and we are going to have to smelt it. Many times it's done in something called a blast furnace. So if you look at the slide, the picture right here, the orange, this is called a blast furnace, and this is what will be used to separate the actual mineral from the impurities. And if you look here, it says at the top, we could take some iron ore. So this is the smelting of iron ore. So here's the rock that contains iron. We're going to use coke. Nope, not Coca-Cola. This is modified coal. It's going to get very hot. And limestone. Please remember, limestone is used to help settle out some of that sulfur. So it's used for purification to help remove some of that sulfur. We're going to get our molten iron down here, and then we're going to end up with something called slag. And so this is the waste material that we have to dispose of elsewhere. It's less dense than iron, so it's going to float on top of the iron. So the waste product from a smelter or from the process of smelting is known as slag. And I'm going to stop here. So I hope you guys have a wonderful day, and you're excited to watch my next video.